Okay, so welcome to this next video in the playlist on calcium signaling. And this video, what we're going to do is we're going to look at an example of an IP3 sensor. So basically, this is the question. We know that IP3 is an extremely important messenger within the cell, and basically it causes a release of calcium from intracellular stores, or at least it primes the IP3 receptors to get ready. And if a little calcium signal comes and calcium binds to those stimulatory calcium binding sites on the IP3 receptor, then the IP3 receptor will open and release calcium from it. So it might be very, very useful to know in the cell what the IP3 concentration is doing and where IP3 is going up and down. Okay, so what we're going to do in this video is look at a way of doing that. Okay, and basically this IP3 sensor is going to use the IP3 receptor. So let's just have a little bit of a revision about the IP3 receptor. So the IP3 receptor sits in the membrane of the endoplasmic reticulum, and it is basically made up of 4 subunits, which are separate proteins, separate polypeptides. So here are the 4 different subunits which comprise this IP3 receptor here. Okay, and each one of these separate subunits has its own IP3 binding domain, basically. And if we look at the IP3 binding domain on each one of these subunits, it has a structure that looks something like this, basically. It has 2 domains, known as the alpha domain and the beta domain, and basically it functions a little bit like a clamshell. When IP3 comes in here and binds, so I'll show IP3. IP3 is in Inositol 145 Trisphosphate, so I'll denote Inositol by this hexagonal ring here, and then I'll have phosphate groups coming off to denote the phosphate groups coming off the inositol. So 145 Trisphosphate. So this is our IP3. So basically, when our IP3 comes into this IP3 binding domain here, what will happen is that the alpha and the beta subunits will close around the IP3 molecule, basically. So what will happen is that it will close like so. So you'll get a closure. You'll bring these alpha and these beta subunits very close together, and it closes around the IP3. And that closure is then what changes the conformation of this subunit and leads to the inhibitory calcium binding site being retracted and a stimulatory calcium binding site becoming available, basically. And that stimulatory calcium binding site then only needs calcium to bind to it in order to activate that subunit so that it will do its bit to try and open the pore, basically. Okay, so this is the idea behind how we can use this IP3 receptor, IP3 binding domain, in order to make an IP3 sensor. So basically, firstly, we do away with the rest of the protein. We just take this IP3 binding domain, and what we're now going to do is we're going to use the principle of FRET, which stands for Fluorescence Resonance Energy Transfer. And this is how, basically, we're going to turn an IP3 concentration difference into a visualizable stimulus. Okay, so this is a Fluorescence Resonance Energy Transfer. And don't worry, if you have never heard of it before, I will explain exactly what the principle of it is. Resonance Energy Transfer. Okay. So the principle is this. We will attach 2 different fluorescent proteins to these 2 domains of this IP3 binding domain. So let's bring the IP3 binding domain down here. Here's the alpha portion domain. Here's the linker portion, and here's the beta domain. Basically, what we can do is we can attach a fluorescence protein to the end of this alpha portion here. So let's attach the fluorescence protein Venus to this alpha subunit. And Venus basically is just an enhanced yellow fluorescence protein. Okay, so it's yellow fluorescence protein, basically. And then we can attach to the beta subunit, we can attach enhanced cyan fluorescence protein. So sometimes people still use the originals, so they still use yellow fluorescence protein and cyan fluorescence protein, but instead often people now use the enhanced fluorescence proteins, and enhanced cyan fluorescence protein is the enhanced science fluorescence protein, Venus is basically just yellow fluorescence protein enhanced, so you could call it enhanced yellow fluorescence protein. Okay, so I'll abbreviate enhanced cyan fluorescence protein to ECFP, basically. So, what is a fluorescence protein? Well, basically, a fluorescence protein is a protein which, if you fire in photons of UV of a specific frequency, so there will be a specific frequency for enhanced cyan fluorescence protein. So if you fire in UV photons of this specific frequency for enhanced cyan fluorescence protein, then this UV photon will be absorbed by the enhanced cyan fluorescence protein, and the energy from that photon will go into the enhanced cyan fluorescence protein. The enhanced cyan fluorescence protein will then re-emit the energy in the form of blue light, basically. So you will see blue light coming back at you if you fire UV photons of this specific frequency at the enhanced cyan fluorescence protein. Now, similarly, Venus is a fluorescence protein, so again you can fire photons of a specific frequency for Venus here. So you have to fire UV photons of a specific frequency at this Venus protein, and it will re-emit to you yellow photons, basically, so yellow light. So if you fire in photons of that frequency, you'll see yellow light coming back at you. Okay, so we put this protein into our cell, basically, and if IP3 is very low, then the protein will stay in this form. So if we fire photons of UV of this frequency specific for enhanced cyan fluorescence protein at the cell, then the photons, some of them, will hit the enhanced cyan fluorescence protein, and the enhanced cyan fluorescence protein will then emit blue light. Now, if these photons hit the Venus protein, they will not be absorbed because it's not the correct frequency, so you will not get yellow light coming back. Okay, now let's say IP3 goes up. Well, if IP3 goes up, it's going to come in here and it's going to bind to these alpha and beta domains here. Okay? And what that is going to cause, it's going to cause a conformational change in this protein. And the alpha and the beta domains are going to shut like a clamshell. So let's draw that happening now. So they're going to shut like a clamshell. So here's our alpha domain here. Let me just get this nice and straight. So there's our alpha domain, here's our beta domain, they're now bound to this IP3 and they're nice and close together. And here is our Venus protein still, here. And here is our enhanced cyan fluorescence protein here. Now, what happens now if I fire in photons of this same frequency specific to enhanced cyan fluorescence protein? So I fire in these photons of UV of this specific frequency for enhanced cyan fluorescence protein, and basically what will happen is the enhanced cyan fluorescence protein will absorb those photons and it will gain the energy. But now the Venus protein is very, very close, as you can see, to the enhanced cyan fluorescence protein. So what ends up happening is that you get some resonant energy transfer. So you get some energy transfer between the enhanced cyan fluorescence protein and the Venus protein. And this is the energy transfer, the resonance energy transfer that is referred to in the name, basically. Resonance energy transfer, FRET. Okay, so now the Venus protein is gaining energy. Now how does the Venus protein emit energy? It emits it as yellow light. Okay, so what are you going to now see if IP3 goes up? You're going to see, well actually I should just complete this, because the enhanced cyan fluorescent protein doesn't give away all the energy, so it's going to still emit some blue light. But basically, if you now fire UV light of this specific frequency at the cell, you're going to get blue light still being emitted, but you're also going to get yellow light. and the amount of blue light you get is going to be lower because some of the energy is going into yellow light now. So this is the way that you can visualize a change or an increase in the concentration of IP3. When there is no IP3, you just see blue light coming back at you. The cell will appear blue, basically. So let's say here is the cell. When there's no IP3, then it will just radiate blue light back at you and will appear blue. But let's say IP3 goes up at a specific patch of this cell. Let's say IP3 goes up here. What you will now see is you'll see some yellow light coming back at you, basically, as well as blue light. So you'll see blue light on top of the yellow light. So you might see green, maybe, potentially. And then blue will be around there, okay? So that is how you can know where and when IP3 levels are going up, because you will see a change in the color of light that is being radiated at you by this IP3 sensor that we've created from this IP3 binding domain of the IP3 receptor.